Welcome to another webinar from the Optical team. I'm Derek Shanks, Product Manager, and I've got another special guest with me today, Christian Grazier, who's a distinguished engineer out of our site in Danderyd, Sweden. We are going to pass it over to him shortly, but I'm going to jump in and just give a couple of introductory slides first. But if you have any questions throughout the presentation, please put them in through the chat, and we'll either get to them during the presentation at the end. We will have time for Q&A, or if we don't get to them, then I'll get back to you after the meeting. So without further ado, if I jump in here, today's topic: Trimble Vision and Trimble AutoLock in the SX10. I just wanted to start giving a brief history of Vision with Trimble. So we have been doing Vision for a long time. Ironically, it was actually in the Trimble GX scanner that we had the first integrated camera, and also had real-time colorization in that scanner. And from there, we moved in and had a first calibrated camera in a total station with the Trimble VX coming out in 2007. Moving on, still on the S series platform, we had the first HDR camera integration into a total station. 2016, we had integration of HDR cameras into our TX series, so the TX6, TX8. And then what we're all here to talk about today, 2016, we had the next generation of Trimble Vision in the SX10, being the blind telescope with cameras as well as a plummet camera. So we have been doing Vision for a while, and it is getting just better and better. The other key topic today being Trimble AutoLock. So I just wanted to highlight a couple of key differences. So we are going to talk on the SX10 behind the scenes and how to get the most out of your instrument. But just to jump back one, on the Trimble S series, it's an analog tracker. So really coarse sensor, just with four quadrants, or with the addition of fine lock options, you can use the inner quadrant, and that works with our active target portfolio, so the MT1000, AT360, and the target ID under the 360 prism. So that's what we had for a long time, what a lot of you know. But then the Trimble SX10, it's a bit of a different ball game. So we moved from the analog tracker to a camera tracker, and that means that it's not compatible with active targets. However, it does mean that we don't need a special mode for fine lock, and Christian's going to go into a lot of detail there, explaining how that all works. And the other key thing is that we can now have a coaxial tracker receiver. So because we don't have a telescope through it, we can put the tracker there, which provides improved stability and performance of our tracking system. We also needed to do this technology shift to accommodate what we needed to get the scanning functionality in with the cameras. But that's just a real brief background. I'm now going to pass it over to Christian, who's going to be with you for the next 40 minutes or so. But yeah, I'll be here able to answer questions and bring them up to Christian if it's relevant. And yeah, sit back, enjoy. And I will just now change the presenter over to Christian.
Show my screen. Spin this one here. Okay.
And Christian, it'd be good if you give yourself a bit of an introduction, but I guess in short, while you're getting your screen up, a long time. There we go. I'll leave it to you.
Is this visible now?
Yep, we can see your screen.
Thank you. So quick introduction. Thank you everybody listening today. I'm working with Trimble since 1997, and first as a manager of the lab in Jena in Germany, and since 2004 I'm technical leader in Danderyd in Sweden. I need to move, I think this one, can't move that. Okay, and need to switch on something as well. Okay, so very quick, going back to what is an SX10? Total station, scanner, or both? And as in the station, typically very accurate aiming, and it's used to selectively capture discrete 3D points. I believe you all know that. And what is the scanner? Yeah, it's to get with speed, many measurements, and it needs a fast beam movement. And finally, it measures a dense grid of points over a target area. So the result is a 3D point cloud. So the SX10 is actually both. It's a true laser scanner with 26.6 K points per second, and it has a range of 600 meters, a distance noise of 1.5 millimeters, and the full dome scan with 10 mega points is done in 12 minutes. So it's a real scan. But on the other hand, it's also a high-end total station. And that's also part of that what I'm concentrating today on. It has 1 arcsecond angle accuracy. It has a distance meter with total station quality of 1 millimeter and 1 ppm accuracy to prism. It has advanced target tracking to follow prisms, and it has a highly calibrated cameras inside. So now we are into today's agenda. I'm going to talk about the vision system and the AutoLock target tracker. And the vision system includes also a plummet camera and a target illumination light. The optical implementation in telescope is seen here. I'm concentrating on the telecamera, which receives the light here through a lens, prism, and focusing lens down here onto the camera sensor. The tracker receives the light in the same coaxial way, focused down to another camera, which is our tracker. Additionally, we have down here 2 cameras that are used for wider field of view. We're coming to that later. So that's the vision system from Trimble. It's fully integrated and a calibrated camera system. It's used for the instrument operation, for documentation purposes, and for measurement purposes. And since this is a scanner, also for colorization of the point clouds for sure. It has got the coaxial telecamera going out through the center of the big eye. It has a primary camera with an average, medium field of view, the overview camera with wide angle field of view, and a plummet camera in the bottom. The visual aiming is an important point for the surveyor. Traditionally, the eye behind the ocular, looking through the telescope, observing the hair cross and getting the target you want to aim to into on the right spot. It's very similar, but still a little bit different. You have no eyepiece, but you get your live video feed on your tablet. And with help of the zoom, you can actually see it very convenient what you want to aim to. You've got a digital hair cross, which is overlaid, and that you by just click on the object you want to point at, and it goes to that spot, and then you can measure. The camera inside experiences as 1 camera, even so it's 3 in physics. It has it's experienced with 8 levels. It has a field of view from 57 degrees of the wide angle camera down to 0.65 degrees field of view. That is an 84 times zoom. Then we have zoom level 7 and 8, which is digital zoom to make the image larger, to be easier to see on the screen. Here another example of the zoom. That's an original image from the SX10 when you store it with Trimble Access, and the object is at 190 meters. That's how it looks like in Trimble Access in the finest physical zoom level 6. And now I'm zooming into that detail here. Just did a screenshot where 1 pixel of the camera is 1 pixel on the screen. You can actually see the screen pixels here. In this, you see the hair cross, and the middle part of the hair cross, that's actually the laser spot. And with that one, you can actually very accurately aim small objects, even at long distances, to get a feeling on what is 1 pixel. It's roughly 1 millimeter at 50 meters distance. So at 190 meters, 1 pixel is 4 millimeters. The digital hair cross is exactly where the EDM points. So it's the middle here. And when you click, the instrument turns to that and measures and adjusts the focus of the telecamera. So this automatic crosshair overlay calculation, which is done in the background, depends on which camera is active, what is the distance to the target, and also sensor data. We're reading temperature inside the instrument, for example. And it depends for sure on calibration data in our production and maybe your user calibration as well. So digital crosshair is distance dependent, especially on the overview and primary camera, which are pointing parallel out from the center. This is a kind of a parallax. The overlaid crosshair position depends on the distance to the object. Here we have the EDM middle, and that's the camera little offset. At distance 1, the ray on the camera is up here. So the instrument automatically moves the crosshair to this spot. On distance 2, it's here, and it moves the crosshair to the right position. We can do that since the EDM is always on. Further, we have temperature compensated optics and high quality glass optics, which is optimized for stability over time and temperature. The telecamera module and the primary and overview camera down here. Remaining temperature influences are then calibrated in our calibration station in production. Not only temperature is here calibrated, but also lens distortion, the lens geometry, the autofocus, and all that on different temperatures. We do that for each instrument individually at -20, +20 Celsius, and +50 Celsius. We do then finally a color calibration to reduce the light fall-off effect of lenses and to make the color look uniform. That's the result after color calibration in production. The aiming using the telecamera in SX10 is able to have the same precision as previously. So you can do in the zoom level 6 very fine aiming, and level 8, 1 pixel is actually 1 arc second. User tests have shown to have the same aiming precision as the S7 total station. And again, you see here in the center cross matches with the distance meter size. After calibration of the camera, measurements in the image are possible. In TBC, for example. And here I'm overlaying on a real camera image what is the calibration error from our production. So here are these errors. At this location, the error is that large, and that is 1 pixel. So this is exaggerated 1,000 times. The primary camera has 1 pixel accuracy at 50 meters, the most accurate one. Here you see a panorama taken with the overview camera in TBC, and it's viewed in TBC here. Can you see the image boundaries here? barely, because they're not enabled, but that's actually the boundaries of the images which are set together in TBC. I'm going into the camera settings now. The camera has settings for white balance, and that helps the system to interpret the scene. So if you select auto, it tries to make the best out of it. And it does not always is the best in auto, because it might misinterpret the scene. If it's a very orange background, it might mean it's warm indoors light. But auto is default and working in the most cases. Overcast means outdoors, overcast at daytime. Daylight is at a sunny day, and incandescent is indoors warm light. Here we have examples where the auto and the manual white balance differs, and the manual for daylight can be really better outdoors. But the auto does a good job. That's indoors auto, and that's indoors manual set to incandescent. You get typically a little better color saturation in manual mode. Another setting is the spot exposure setting. That's especially important when the target is brighter or darker than the rest of the image. And here in the middle is the target. It's actually brighter than the rest. And without spot exposure, it's barely possible to see the car railing here. But setting it to spot exposure, a small SE, is visible in the hair cross. Then it takes this small area of the big image to calculate the exposure time. And then you see all the details nicely exposed. We have a fourth camera, which is in the bottom of the instrument. You see here, that's a plummet camera. It goes through the center hole, and the purpose is to look to the ground mark. And yeah, the resolution is good, and you can see details such as around 0.2 millimeters on the ground. It's very accurate and stable, and it gives you an easy access to the ground mark. A further feature of the cameras is the target illumination. That is a scene seen by the camera when the target illumination is off. And it might be difficult to find where are the prisms which you wanted to aim. Maybe your colleague has set them up and you've got only a map, and where are these? Where are those prisms? Switching on the target illumination, you actually see one prism here, one prism there, closer one by here and there. So this helps actually to find and select the right target, especially when the surrounding work. So when you are done and know everything about the camera, you want to know maybe in the field, how can I trust the cameras in field? How can I do the in-field check of the cameras? And it's easy as 1, 2, 3, as my colleague Torsten showed last year on dimensions, these slides. Aim the target in phase 1, switch phase, and check how much it deviates in phase 2. In this example, it's actually 5 pixels. And in that case, yeah, maybe you should do a user calibration. But how to do that? We optimized that field calibration of the camera center point. And how is it working? I'm going to show now. So the field camera calibration uses a kind of a template matching algorithm. What is that? Actually, a template is cut out from an image, and then we try to find where this template is located in instrument phase 1 and phase 2 in the images. So this algorithm looks computer vision algorithms and can find it for you, so you don't have to click into the details. And here I show you how is it working in the instrument. We take a series of pictures in phase 1, and we actually check if leaves are in the images and something is moving. We would detect that and say it's not a stable target. That's not good for calibration use. So we select a small area around the EDM beam and taking pictures from that. So we take pictures in phase 2, rotate it back internally and try to match that pixels to the images from phase 1. And then we get actually a strength of match value for each of those pictures. And the best matching position, phase 2, is calculated in pixels. So the offset between images from phase 1 and phase 2 images in phase 1 is determined. And this little delta then is the collimation area, which is applied to the camera center. What is needed that this works? Actually, we need features because the algorithm need to find something in the images. The well would not work. But what is working? Would that work? Yeah, if you select it here, not so good. It's a linear feature. Because the camera is an area, it needs actually features in 2 directions. So that's a good feature. That would work perfect. The plummet camera has the same principle, and it needs, in the same way, 2D features. It could be even that rough features would work perfect, and it does not need to be very leveled to work. But we have some limitation here as well. It should be no depth difference in that small area when you do the calibration. So phase 1 would look like that, add some depth, and phase 2 like that here. That's because of the parallax. The images would look very different, and the algorithm cannot make a calibration on that. So the suggestion is to have more flat depth in the target for the calibration. If you have questions to that, come back to that later. Now I'm moving on to the AutoLock system. The SX10 AutoLock system does not inherit the S-series tracker. Actually, it was impossible to combine the optical setup which is needed for the scanning beam deflection with the tracker which we have in the S-series. So we moved on with technology to camera sensors, and those have improved greatly in recent years. And the available computation power needed for a good tracker performance and also for smart decisions, which is a good target, which is not a target, are now available. So how does now our tracker find and tracks a prism? So first we're sending out with this little prism the laser beam onto the target. And yeah, looking back from the instrument to the target, we have some sunglasses. We call it narrow band pass filter. And then we're using a kind of a difference image. So one image was on and one was off of the laser, and it generating the differences. We have an intelligent target detector that does not view and look at reflex west signs. It looks only at the prism. I'm going to show you more about that. And it does even suppress false targets that might look like that, headlights, of course. It has a predictive tracking, which also is present from the S series. And it has a fast target search. So again here, that's the movable tracker transmitter in the middle. It needs to be moved out. You have seen that while the scanning is operating. In total station mode, it's in the center. So now something about the sunglasses which we need. The solar spectrum is very, very, very wide. It has a lot of light in the visible area, but also infrared light. How should we be able to see when 1000 watt comes down to Earth from the sun, a little laser, which is 1 million times lower in power? What we do is we use a camera chip that sees only a portion. We have then a very special camera filter that cuts out all the rest, and we are looking only at the specific wavelength. This is a filter for special Trimble design. So that's our sunglasses. Then we have a second effect is we're illuminating the target and getting a picture back. We're seeing the target here. But then we take a second picture without illumination and we do subtraction. Now it's more clear. And this little blob can then very accurate be evaluated where is the center of this blob and how does it behave. We do that actually with 100 frames per second, which allows a very fast tracking speed. So let's now look how the tracker detects the target. The field of view of the tracker is very similar to that of the telecamera. Up here, you see a field of view of the telecamera. And down here, I have overlaid images from the tracker. Actually, a little later, you see videos both on telecamera and trackers, which is in the special R&D mode recorded. So the tracker blob is detected, and we're doing a center of gravity for that. And we are evaluating the size, the shape, and the motion of the target. And then that target that is most likely to be your target, that one is tracked. So what can be false targets? Other reflectors, road signs, reflective vests, but also quickly moving bright objects. First point, false target. So that's, you see here one target that's on the rod, and the other that's a target which is in the background. And you see the tracker detects both. And the camera tracker actually has an inherent fine lock. So it's no problem to move very close by. You're going to see now a video which is repeated 2 times. Let's see how full it starts here. And you see how the tracker keeps lock on the right prism. And you see how close by the prism goes the other one. So it's actually no problem to have prisms close by anymore. Okay, let's go on to the next step. I've showed this picture earlier. Road signs in the background on long distance. No problem, even if the road signs are large. The reflex coming from the prism is very strong, and the small pixels read only the power from the prism. The power coming from this big sign is smeared out on the many pixels of the tracker. And you're going to see that in a kind of a video again. He's walking even behind that target, and the predictive tracking follows nicely. Second time here. Now I've actually stored one picture because it went so fast. When the target is behind the street sign, the tracker sees actually a little bit of the street sign, but it can actually distinguish that from the real tracker. So it's not reacting, not failing. Another situation which could be a problem is headlights. Since the car is moving while we're doing the differential images, the car headlight changes, and we're going to see that what happens. It looks like it's always on the prism. Have you seen anything in the video right on the right side? Let's take a still, which one is stored at this situation here. You see the headlight, which is strong, and since it's an infrared source in the car headlight, it's been seen by our tracker, but it's a different shape. It's this little bit different image of the movement, and it's just the tracker's not reacting on that. Now we're doing similar things on the long distance, and here you see very strong sun reflexes, and the car is moving. You see that here, and it's not disturbed, even that's in the field of view. The tracker is so sensitive that this is stronger than the strong sun reflexes from the car here. I'm going to show you now a little video on predictive tracking. So he's walking behind the sign pole and is following, and now it's going behind the tree, and it continues with the previous speed. So it just continues in the same way. And actually you can do settings, how long it would, once more. Okay, here comes the setting. You can do the setting for the predictive tracking time, and you can set it to 3 seconds depending on your disturbance in the field of view, or 5 seconds. But these are good values. So if it would not be visible, the target after this time, the instrument would point back where it was left off. And you could go back. Or you could switch on the auto search, and you can define here the search range. Now I'm going to show how automatic search looks like. On the left side, the tele image. On the right side, you see what the tracker sees. And now he's going behind leaves, and then, oh, he should have higher target. So it was lost and was outside the predictive time. Searching goes around and sees a lot of other reflexes, but it finds out that those reflexes are not a prism, and it hunts back to the original position where it lost lock. So if you see that it loses lock, Trimble Access tells you target lost, just stay where you are, raise your prism, and maybe type in your new, not maybe, you should type in the new instrument height, target height, and then it will lock on again. Here are the search window settings. So to summarize on that here, we did significant improvements in passive tracking in the SX10. It now distinguishes between targets very close together. It's not sensitive to reflective vests or road signs. The tracker is more intelligent of tracking targets in areas with many prisms, like FineLock, or even better. A platform, the new tracker is a platform for future with enormous potential for improvements. Improvements in camera sensors, but even more intelligent algorithms. So for normal use, no active targets are needed with the SX10. And with that, I am done so far with my presentation, and I'm looking forward to your questions.
Yeah, we've got a couple coming in here, Christian. The first one we'll start with. So we talked about how there's 8 different zoom levels in the field software, and just wondering, so it's up to zoom level 6, that's optical. Do you want to just talk to the optical versus digital zoom there for a second?
Okay. Yeah, what does optical zoom level means? We have 3 different cameras which have different optics. That's really optical. And in the telecamera, when we go into the other zoom levels, we actually cut out the center part of our 5 megapixel sensor and displaying that as a video stream. And that's also the reason when you press store image that you get different image sizes. So if you press store image in zoom level 1, you get a 5 megapixel image. But if you do that in zoom level 2 or in zoom level 6, you get a smaller image, which is not 5 megapixels. That's not a digital zoom, that's physical zooming into the sensor. 7 and 8, that's actually zoom levels which we interpolate the pixels to show them larger on the screen. Otherwise, you would have difficulty to point with your finger or with your pen on the right location to aim accurately. And you could also use the arrow keys to aim accurately, since one arrow key step maybe is then 1 arc second in the zoom level 8.
Cool. And then there's a question around which prism is best to use with the SX10. So as always, a Travis prism is, single glass prism is going to give the most accurate measurement. However, for general topo work, of course, the 360 prisms are going to be the best, because then you don't have to worry about orientating towards the instrument, but you do lose a wee bit of accuracy. I don't know if you've got anything else to add on which prisms work best with the SX10, Christian?
Yeah, I think you said actually what's the case. Most accurate you get it on the traverse prism and single prisms. Actually, our algorithms are looking into the 360-degree prism to get the best of the center of gravity, which makes that accurate. And if you're out and with a 360-degree prism and you want to be very accurate, you actually could turn one prism towards the instrument. Then the accuracy is not only 2 millimeters on the prism, could go down to 1 millimeter.
And then there's a few questions all around sort of the same topic that I'm going to try and answer, but then I'll let you, Christian, add anything at the end around detecting multiple prisms or locking onto different prisms. So once you're locked onto a target and moving around with it, if that target never gets obscured, then the tracker is going to be able to continually track that target. So that's where Christian was showing, car headlights or other targets can come into the field of view of the tracker, but it won't lock onto them because it can track and maintain the original target that it's locked onto. Where you'll find it locks onto a different one is when, if something obscures your original target, then it will look for any other reflection in the in the tracker sensor, and so if it sees something else, it'll turn and lock onto that. But so if your target that you're currently tracked gets obscured, then that's when it will look for something else. But if it never misses locking onto that, then other things can come and go from the tracker sensor, but it's going to be able to distinguish from that.
Yeah, it's completely right. And there I have a trick. When we measure through heavy traffic, actually it's good to switch off the auto search. When you see, oh, there's a lorry coming and blocking for 5 seconds, just stand still and let the lorry go, and it will lock directly after the lorry is passed in the field of view. So the search should be switched off in such busy cases.
And then there's also a question around reflective targets, black and white targets. So with reflectives and black and whites and all that, we use, you need to use DR mode to measure to, so there's no one specific target that we recommend using for reflectors or black and whites. It's just all done through DR mode, pointing through the camera system. I don't know if there's anything else you want to add on that one, Christian. Will I have a look at a couple more questions that have just come in?
If you want to aim accurately to the reflex sheet targets, the line of the reflex sheet might be a little thin for the telecamera. So actually, when you have to point on a reflex sheet on 100 meters, you should actually make the line, the middle, thicker, but you can see that with the telecamera. Then that would help. So a 5 millimeter line at 100 meters is perfect to be seen.
And then still on the prism track, a question around any issues tracking peanut prisms. So it's just a case of if the tracker sensor can get a reflection from the prism, it's going to be able to lock onto it, correct?
Yeah. And the range might be limited then, since the signal is smaller from a small prism.
And that's because the bigger the prism, the more light it can send back to the tracker from where it comes, whereas the smaller prism, it'll not be as reflective, so to speak.
Yes, that's right. And there's another parameter, which is the quality of the glass prisms. If you really need the 600 to 800 meter range, you should have 50 millimeters prism of the really best quality which you can get. So not thinking, okay, it's a 50 millimeters prism, it's cheap, it will work. No, it needs to be really good, the Traverse prism from Trimble.
And then one other one here, just talking about how the crosshairs displayed in the video. So can you just talk to how the crosshairs calibrated in relation to the cameras?
Yeah, I went into that during the presentation. So the crosshair is calibrated in production here for all the influences that could occur. The crosshair is always where the EDM is. In our production, the EDM sets the measurement beam. Yeah, that's where your distance is measured. And we see in our production the distance meter beam. And we see as well the hair cross, and we can set this accordingly. Also for temperature variations, we do that calibration and so on. That means that hair cross is going to be digitally overlaid. Was that the question, or is it a different question in the background?
Yeah, no, that was good. And then if you want to, Christian, pass the presentation back to me in that panel on the right. I've just got a couple of wrap-up slides I'd like to show.
I'm not sure how to do that. Click to stop screen sharing. Now stop the screen sharing.
Okay, and then...
You want to have the presentation right?
Yeah.
Yeah.
There we go. Perfect. Yep. So I'll jump into this one here. So I just wanted to highlight that on our geospatial.trimble.com webpage, there is a whole lot of resources available for you, and in particular on the SX10. If you go to the SX10 page and then under downloads, there's a whole bunch of bulletins, info sheets that we've put together on a lot of the topics that we've covered today, such as the plummet camera, the till light, an in-field calibration guide that goes into step by step on how to do the camera calibration that Christian talked about, and also I just want to highlight that a new firmware version is available for the SX10 that was released a couple of days ago, so hot off the press, S2.2.25 available through Trimble Installation Manager. The feature of this firmware release is that you can now change the Wi-Fi channel selection if you have Trimble Access 2019 or newer, so that allows you to choose between 1, 6 and 11 for the channel that the Wi-Fi will connect on, so that can be helpful in congested environments, using your SX10 to switch channel if one's using doesn't have as much traffic on it. Also, if you're operating two SX10s on a site, then you would want to you would get improved functionality by having them on separate channels. But yeah, do check out the download section, and also make sure your SX10 is running the latest firmware for all the best features. Also, just wanted to highlight on our webpage, geospatial.trimble.com, if you go /accessories, we'll take you to the slide on the left where we have now all our GNSS, our optical and our scanning accessories, and controller accessories are coming very, very soon. So here on the right you can see the different tabs showing all the different prisms we have, the tri-racks we have, so you can see all the accessories we have to go with our different instruments, all there on our web page. Also, just want to highlight the resource center. So on the main geospatial.trimble.com page, on the resource center at the top, you'll see lots of different good things, but there's two I want to highlight is both a blog and the webinars. So we did a webinar on the scanning and the EDM principles in the SX10, so that's up there on webinars. This one will be available there shortly, this recording, so you can download and watch it again or send it to your friends, and also a blog that has a lot of good tips and information coming out, also new products and stories. So yeah, I encourage you to go and check that out. I think it's the last slide I have. We now have the ability for you to request a demo, in particular on the scanning side. So if you go to trimble.com/scan-demo, you will get to the page on your right where you can fill out your name, address, your email, select what you're interested in a demo on, and then we will make sure that happens. Alternatively, just through the main website, through products and solutions, choose laser scanning, and then you've got the big request a demo button. So that's also there to help you make sure that you are seeing and getting all the best out of our equipment. And I think that's what I had. So I'll just have a quick check to check that there's no new questions that have come in. I know there's a couple that I'll get to offline. No, that's good. So Christian, thank you very much for your time. Thank you everyone for joining. Stay tuned for another optical webinar, and hope you have a great day, and thank you very much for calling in.
Thank you. Bye bye.